we can see, can we stop earlier? So you may be wondering, do we really have to go through for a graph of v vertices v minus 1 iterations? So when can we stop earlier? So that's the question. So anyone can say or type the answer. I think you can use your microphone too. So can we stop in when can we stop in an earlier iteration? So if you see this second example that we just went through, the estimated path weights changed for at least one vertex between two successive iterations. So initially we had 0, infinity, infinity for everything, and for this iteration at least one entry changed from infinity to 3 and infinity to 8 and so on. The second iteration, this entry changed for v4, it changed from infinity to 2, everything else remained the same. Then the third iteration, we got a change from, for v3, changed from 8 to negative 3, everything else remained the same. Then for iteration 4, it changed from v2 to v1, and that was last required iteration. We don't need to go through any further iteration. So far in the examples that we went through, in each iteration at least one entry changed, so we went through all the required v minus 1 iterations. Now I have a third graph as a practice, so I let you to do this example for practice. Excuse me. So now if you look at the numbers here for the estimated path weights, it is again initially 0, infinity to everyone, and then the first iteration you find these as estimated path weights. So at least one entry changed, like what, infinity to 3. So we'll go through second iteration. Now at least again here one entry changed, so from infinity changed to 10, infinity to change to 4, infinity to change to 6. Now when you do the third iteration, you see that none of the entries changed. So between the two iterations, 0 same as 0, 10 same as 10, 3 same as 3, 4 same as 4, 6 same as 6. So it means the entries did not change from the second to the third iteration. So which means even if you do one more iteration, it's going to remain the same, because you see what we are doing in each iteration. We are using the estimated path weights from the earlier iteration, from the previous iteration, to see if we can reduce the estimated path weight in the current iteration. And if we are not able to reduce estimated path weight for even one vertex in the current iteration like this, so we had these values as estimated path weights from the earlier iteration, and at the end of the third iteration we are still ending up with the same estimated path weights. That means we did not really reduce estimated path weight for any vertex. So if you want to run the fourth iteration, what we are going to do, we are going to still write the same estimated path weights as the path weights for the vertices, and then try to see if you can reduce the path weight further. You're not going to be able to do that, because still you're going to say the minimum of 10 plus 2 and 4 plus 6 is 10, and we stay with 0 that we know. The minimum of 3 plus 7 is 10, is same as 10. 0 plus 3 is 3. 3 plus 3 is 6, 4 plus 5 is 9, the minimum is 6, so we stay with 6. So we are not going to be able to reduce estimated path weight further. So that's why we can have, say, a boolean to keep track of whether the entries in the estimated path weight vector changed in the current iteration compared to what it was in the iteration. So if none of the entries changed for any vertex, that means we have found the shortest path from the starting vertex v1 to all the vertices. So we can stop the algorithm at that iteration, and we do not need to proceed to the subsequent iteration. So even though it might be earlier than v minus 1 iterations, like in this case this is a graph of 5 vertices, so we have to go through at the worst case 4 iterations. But like in this example here, using this optimization principle or idea, that if none of the entries changed in the estimated path weights for in a particular iteration, that means we have found the shortest path weights from the starting vertex to all the vertices, so we can omit the subsequent iterations. So that is the optimization that we can do for Bellman 4. So again, it's not guaranteed for any graph. It depends on the graph. So like in the first two examples we went through, we have to go through all the 4 iterations. Whereas here we can stop in the 3rd iteration. Okay. So this is sometimes saving can do for Bellman 4, but still at the worst case it's the E times V time complexity compared to E times log V for Dijkstra's algorithm. Okay, so among the two, between the two algorithms, Dijkstra's algorithm is better, but remember the advantage that we have with Bellman 4, it can be used with negative edge weight also. So let me stop here for